Welcome to ring theory. Today, we are exploring a beautiful and powerful concept, unique factorization in polynomials with integer coefficients. Imagine having a massive bucket of basic Lego blocks used to build a complex toy castle. Just as you can break that castle down into fundamental, unbreakable blocks, we can do the exact same thing with algebraic expressions. We will learn how to break down polynomials into their absolute most basic prime pieces, a process that forms the bedrock of modern algebra and even computer security. Let us dive in. To begin our journey, we first need to define the mathematical workspace we are operating in. We denote this space with the symbol Z adjoined with X. The letter Z represents the set of all integers, meaning positive and negative whole numbers, including 0. The X indicates that we are building polynomials using this variable. Therefore, this space is simply the collection of all possible polynomials where the coefficients are strictly integers. In this specific workspace, an irreducible polynomial is the algebraic equivalent of a prime number. It is a polynomial that absolutely cannot be factored into two smaller polynomials that still have integer coefficients. Understanding this environment is crucial before we start breaking things apart. Now that we understand our workspace, let us look at the main theorem itself. The concept of unique factorization guarantees that if you only use whole numbers, there is exactly one specific way to break down any polynomial into unbreakable pieces. It states that every non-zero polynomial in this set can be written as a product of a constant integer and one or more irreducible polynomials. More importantly, this specific combination of factors is completely unique. In simpler terms, no matter how you choose to break down a polynomial, you will always end up with the exact same list of fundamental building blocks at the very end. It is the exact same comforting rule we have for basic arithmetic, upgraded to work for algebra. Before we can actually use this theorem in practice, we must introduce a vital tool called the content of a polynomial. The content is simply the greatest common divisor of all the integer coefficients present in the polynomial. For example, if all the numbers in your polynomial are even, the content is at least 2. When a polynomial has a content of exactly 1, meaning its coefficients share no common factors other than 1, we call it a primitive polynomial. We can always factor out the content from any polynomial to leave behind a primitive polynomial. This clever step allows us to completely separate the purely numerical part of the polynomial from the algebraic part, making our factorization process much easier. This separation we just discussed can be expressed with a very simple but powerful formula. We write f of x equals c times g of x. Conceptually, this formula splits our factorization problem into two much easier tasks. The symbol f of x represents our original starting polynomial with integer coefficients. The symbol c represents the content, which is a single integer pulled out from all the terms. Finally, the symbol g of x represents the remaining primitive polynomial, which now has a content of exactly 1. As the value of c increases, it simply means the original polynomial had larger common factors among its coefficients. However, the algebraic structure of g of x remains completely independent of this scaling factor. Now that we have our formula, we need to understand the secret engine that makes this entire theory work, a famous mathematical result known as Gauss's lemma. Gauss's lemma states that if you take two primitive polynomials and multiply them together, the resulting new polynomial will also be primitive. This might sound like a minor detail, but it is incredibly powerful. It guarantees that the algebraic parts of our polynomials do not accidentally create new common integer factors when they interact. Because of this lemma, we know that if a polynomial can be factored using messy fractions, it can always be factored using clean, simple integers instead. This lemma is the theoretical bridge that proves our workspace is indeed a unique factorization domain. Before we move on to more abstract ideas, let us see this step-by-step breakdown with a concrete example. We are given the polynomial f of x equals 6x squared minus 6, and we need to find its unique factorization. Our strategy is to first find the integer content, factor it out, and then break down the remaining primitive polynomial. Looking at our starting polynomial, we examine the coefficients, which are 6 and negative 6. The greatest common divisor of these two numbers is 6. Therefore, we determine that the content of this polynomial is 6. This is our crucial first step before we tackle the algebra. Continuing with our problem, we now factor out the content of 6 that we just found. The expression inside the parentheses becomes x squared minus 1, which is our primitive polynomial. Its coefficients are 1 and negative 1, sharing no common factors other than 1. Next, we must factor both the outside integer and the inside polynomial separately. We break down the integer content into its prime factors. The number 6 factors uniquely into the prime numbers 2 and 3. Then, we factor the primitive polynomial. We recognize x squared minus 1 as a classic difference of squares from basic algebra, which factors cleanly into x minus 1 and x plus 1. Now that we have factored both parts, we combine all our pieces together to get the final result. The original polynomial, 6x squared minus 6, has been uniquely factored into 2, 3, x minus 1 and x plus 1. Because these new polynomials have a highest power of 1, they cannot be broken down any further. They are completely irreducible. No matter what method you use to solve this, you will always end up with these exact 4 fundamental building blocks. This perfectly demonstrates the unique factorization theorem in action, showing how a complex expression reduces to a single, undeniable physical reality. To really cement what we just did, let us look at a visual summary of the entire process we just performed. At the top of this flowchart, you see our original complex polynomial, 6x squared minus 6. Notice how it splits into two distinct branches, a purely numerical branch on the left for the content, which is 6, and a purely algebraic branch on the right for the primitive polynomial, x squared minus 1. Each branch then continues to break down downward until it hits rock bottom. The 6 splits into the prime numbers 2 and 3, while the algebraic part splits into the irreducible polynomials x minus 1 and x plus 1. This tree structure is a perfect mental model for how unique factorization operates. Now that we have a solid mental model, let us tackle a slightly more complex example to understand how negative signs fit into the idea of unique factorization. Suppose we are asked to completely factor the polynomial negative 4x squared plus 36. Our approach remains exactly the same. Extract the content, factor the integer, and factor the primitive polynomial. We examine the coefficients, which are negative 4 and 36. The greatest common divisor is 4. However, it is standard practice to factor out a negative sign if the leading term is negative, to make the remaining polynomial easier to work with. So, we will factor out negative 4 as our content. Following our strategy, by pulling out negative 4, the remaining primitive polynomial becomes x squared minus 9. Notice carefully how the sign of the second term flipped from positive to negative. Now we break down the integer part and the polynomial part. We factor the integer negative 4. The prime factorization of 4 is 2 times 2. The negative sign is treated as a unit, which is a number that divides into 1 perfectly. In the integers, the only units are 1 and negative 1. We keep the negative 1 separate to show the prime factors clearly. This ensures our numerical foundation is perfectly prime. For our final steps in this problem, we factor the primitive polynomial, x squared minus 9. Once again, this is a difference of squares. It breaks down cleanly into x minus 3 and x plus 3. Both of these are degree 1, meaning they are irreducible. We combine everything to reach our final completely factored form. The polynomial is factored into negative 1, 2 squared, x minus 3 and x plus 3. Physically, this tells us the exact roots and scaling of the polynomial curve. Every single piece is now in its most fundamental, unbreakable state, completing our factorization. Looking at that last answer, this brings us to an important question about uniqueness. You might wonder, what if another student wrote the answer with a positive 2 squared but changed the algebraic part to 3 minus x? Are these two different factorizations? The theorem says they are exactly the same. The second student simply multiplied the negative 1 unit into the x minus 3 term to flip it. In ring theory, factorizations are considered unique even if the pieces are multiplied by units like negative 1 or rearranged in a different order. The core building blocks remain identical, preserving the absolute truth of the theorem. Now that we have mastered the mechanics, you might ask why this abstract algebra concept matters in the real world. It actually forms the absolute foundation for modern cryptography and computer security. Many advanced encryption systems, such as lattice-based cryptography used to protect data against quantum computers, rely heavily on multiplying and factoring massive polynomials. If polynomials could be factored in multiple different ways, decryption algorithms would completely fail. A single encrypted message could be interpreted as several different original messages, destroying the security and reliability of the system. Unique factorization guarantees that when a computer decrypts a polynomial message, there is only one true answer. We have covered a lot of ground today, so let us summarize the most important ideas. First, unique factorization in polynomials with integer coefficients is the mathematical guarantee that these algebraic expressions behave just as predictably as regular whole numbers. Second, by separating a polynomial into its integer content and its primitive algebraic part, we can systematically break it down into irreducible components. Finally, thanks to Gauss's lemma, we know this breakdown is absolute and unique. You have now seen how these abstract building blocks provide a stable foundation for both theoretical mathematics and applied computer science. Excellent work today.